Good morning, afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar. Eliminate DC to DC converters in multi-output power supplies to achieve high efficiency and excellent output regulation. Brought to you by Tech Online, Power Integrations, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You may participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area, hit the submit button, and please note that we'll try to get to as many questions as we can in the time we have today, but if we don't get to your individual question, someone will get back to you after the program is over. At this time, we recommend you disable your pop-up blockers. And at the end of the webinar, we'll ask you to complete our feedback form. And your feedback will provide us with valuable information on how we can improve future events. And if you experience any technical problems during this webinar, just type your issue into the Q&A text area and hit the submit button. We'll be glad to offer one-on-one assistance. And now, on to the presentation. Eliminate DC to DC converters in multi-output power supplies to achieve high efficiency and excellent output regulation. Discussing today's topic is Han Sui, Senior Applications Engineer at Power Integrations. Han holds a master's degree from the University of Southampton and a bachelor's degree from the University of Nottingham. Prior to joining Power Integrations, she worked at Delta Electronics in China and TDK Lambda in the UK. It's with great pleasure I now hand things over to Han to begin. Han, take it away.
Thanks, Colin. Hi, good morning, good afternoon, and good night again, depending on where you are. So let's begin. Half of the power supplies being shipped worldwide are actually either adapters or chargers. And among the other half, there's one thing in common. Almost all of them require multiple outputs. And flyback is the most common topology for offline converters. That means it's really important for us to know how to get multiple outputs with flyback design. So in this presentation, I'd like to focus on talking about a new way and a revolutionary new IC to help us achieve multiple outputs with flyback design. Sorry, got a bad cough. We don't need to use any DC to DC post-regulators. That means we get to save on the efficiency compromise. We'll have high efficiency and accurate regulation at the same time. So without further ado, let's begin. Before jumping into the new solution or new way of achieving multiple output flyback, I'd like to talk about the existing solutions that we've got. So when we talk about multi-output flyback, we're normally referring to one of the two solutions. And the first one is the simplest one, which is a multi-winding flyback with no DC-DC. That means you can simply just wind multiple windings on the secondary side of the transformer to be able to get multiple outputs. This is a really simple solution. Cost is quite low. However, the regulation on the system is not going to be great because you normally just get good regulation or accurate regulation on one of the outputs. The rest of the outputs won't have great regulation. So what happens if you want accurate regulation on more than one of the outputs? Then you'd have to go for a flyback plus DC-DC, where you simply just add the DC-DC post-regulator to get great regulation on the output that you want. So in this case, you solve the accurate regulation issue. However, the additional DC to DC circuit means you have to compromise on your system efficiency because of the second stage of power conversion. And also other problems coming along with the DC-DC is that you have to add on component count in the system. You might have to use a larger size PCB, and you'll have to add on the cost of the system. So none of these are really ideal. So how do we tackle these limitations with the existing solutions? Then we came up with this new IC that's called InnoMux-2. Here's the schematic. As you can see, this is a single stage flyback, and yet you have multiple outputs with accurate regulation. There's no need for any DC to DC post regulators, so you get to get good efficiency at the same time. So in this presentation, I'd like to introduce a a bit more about what InnoMux-2 is capable of, and at the same time talk about how InnoMux-2 works and how we can deliver what we can deliver. So before jumping into the operating principles, I'd just like to cover a bit more details about what InnoMux-2 as an IC is capable of, a bit more information for you. So over here is the schematic of InnoMux-2 again. And as you can see, it's a single stage, single chip offline flyback switcher specifically designed for multi-output flyback. And we have only one stage of power conversion over here. That is the main flyback stage. And yet we have two outputs, and each individually regulated, accurately regulated, independently regulated too. So we don't need any DC to DC post-regulators, as you can see on the schematics here. And the first thing you notice by removing all of the DC to DC post-regulators is, of course, the efficiency gain. The efficiency gain with using InnoMux-2 can be up to 10%. Also, it comes with reduced PCB area because you don't need any of the post-regulators anymore. And of course, the part count reduction as well. The component count reduction can be up to 50% using InnoMux-2. We talk about accurate regulation. So we offer plus minus 3% regulation on all of the outputs. What does that mean? This 3%, plus minus 3%, has already included all of the worst case conditions, basically including across load and line, temperature tolerances, and board-to-board production tolerances. We can support up to 3 outputs, including constant voltage output or constant current output. We'll talk about the detailed applications that we can support in the coming slides. Next thing with InnoMux-2 is that due to its unique single-stage power conversion, we can actually achieve excellent standby performance. This is because think about using traditional multi-winding flyback or flyback plus DC-DC. Both of these solutions, in order to regulate the output accurately at very light load, you might have to add on dummy load into the system. So for example, if you use a buck circuit as the DC to DC post regulator, in order to regulate the output at, for example, no load, you'll probably have to add bleeder circuits. So the bleeder circuits for buck or the dummy load for the multi-winding flyback, all of these will add on constant power consumption, which makes it hard to design good standby performance with these solutions. But InnoMux-2, because of its single stage, and also we can accurately regulate these outputs without the need for any dummy load. That means we can get excellent standby performance. It's going to be less than 50 milliwatts with no load input power consumption. And by eliminating all of the dummy loads, we give you 20% more standby power. A little bit more details about the IC itself. So here is the InnoMux-2 IC that has the primary side and the secondary side in one package. And on the primary side, we have a integrated 750 volt power GaN switch. It can also be a 650 volt or a 725 volt silicon MOSFET, depending on your needs. The power range is from 15 watts to roughly about 100 watts without PFC front end. This is with high line only. InnoMux-2 comes in a proprietary power integrations package, the InSub-24 or InSub-28 package. It's very thermally efficient. And what we can do is to simply use the source pin of the package here, connect it to the PCB, add a bit more copper pore area to fully utilize PCB cooling. And by doing so, we don't have to use any heat sinks anymore. And this can be specifically advantageous for some applications with certain constraints. For example, they have space constraint, or they simply just don't want to use any heat sinks because of the cost. So InnoMux-2 allows you to go without the heatsink. We did talk about removing the DC-DC, having just a single stage power conversion, giving you higher efficiency. And yes, we can offer the highest efficiency in the market because of its unique power architecture. Not only that, we can offer even further efficiency improvement with this additional feature, 0 voltage switching on the primary side switch. Normally, if you want to achieve 0 voltage switching on the primary side switch, we'll have to use active clamp circuit. But in this case, with InnoMux-2, we don't have to use any additional circuitry. We simply leverage the existing SR, synchronous rectifier, on the secondary side to be able to achieve this feature. I'll talk about this in detail about how it works and what does the principle look like in the coming slides, and we can expand on that. We also, like I said earlier, we use PowiGaN primary switch that has very low RDS on, that ensures high efficiency, of course. We have integrated FluxLink inside the IC package, and FluxLink is a PI proprietary barrier crossing technology that sits across the primary and secondary side of the circuit. Basically, by having FluxLink, you don't have to use any optocouplers anymore. That increases system reliability and also reduces part count. For a lot of power supply designers, especially for multi-output power supply designers, they are quite interested in knowing the protection mechanism for the power supply. Because for multiple outputs power supply, designers still want to be able to protect each output from its own overload condition. But this cannot be done with a traditional flyback, or let's say traditional multi-winding flyback. Because for a traditional multi-winding flyback, the power supply sees the whole secondary as one thing rather than being able to differentiate different outputs. So you can only protect the whole unit as a whole unit itself. But InnoMux-2 is able to protect each output from its own overload condition. And we also provide a gross protection for the whole unit itself. So before going into showing you the excellent regulation and high efficiency data, I'd just like to touch upon the market driver. Why are we going towards InnoMux-2? What is driving us towards going for InnoMux-2? I'll give you an example here. This is the energy-related regulation in Europe for household appliances. And they're going to reduce the off-mode power consumption from 500 milliwatts to 300 milliwatts. This will be effective from 2025. So what does this 200 milliwatts mean to us designers? If we stack up all the numbers here, the average households in Europe, almost 200 million, and the average home appliances for each household being almost 14. If we stack up all these numbers, it gives us a 4 terawatt hour, or which is equivalent to 1.155 billion euros energy saving by the year 2030. And this is a huge number. That's exactly why the whole industry or the whole world are pushing towards going to highly efficient power supplies. And when I say highly efficient, it's not just highly efficient at run mode, it's also highly efficient at standby mode or no load mode. No load condition. Okay, so we keep talking about, I have been talking about accurate regulation. So what does it actually look like? Here are some test results. So the difference between InnoMux-2 and traditional flyback is that InnoMux-2 works differently in a way that it only delivers power to the output that's requesting it. That means different, because for a traditional multi-winding flyback, every time there's current discharge on the secondary side, you can't help but all of the outputs will get a part of the energy, and that's what we call the cross-regulation issue. But with InnoMux-2, we don't have that anymore because we strictly control which output gets the energy that they want. So this test data is based on a real application with dual output power supply. It has two constant voltage outputs, a 5-volt and a 12-volt. So the test condition covers across load and line changes. Line is from 90 volt to 265 volt. And load is from absolutely no load to absolutely full load on both of the outputs, so 5-volt and 12-volt. So with all of these changes, we can still maintain the regulation accuracy on both outputs to be within plus minus 1%. I'd just like to be a bit more clear on the data over here. So let's have a look at one set of data over here, for example. This is the 5-volt output. So this is when 5-volt is being loaded with 20% load. And this set of data includes, of course, the line changes from 90 to 265 volt. And it also includes load changes on the 12-volt output. And on the 12-volt output, the load changes from absolutely no load to absolutely full load. So this set of data has included all of that. So even with all of that, you can see there's no issue with cross-regulation because our regulation accuracy is still staying within plus minus 1%. Okay. This is the case study on efficiency gain with using InnoMux-2. Again, it's based on a real project where a 5-volt constant voltage output is needed and a 29-volt LED constant current output is needed. So this application is for display. And competitor solution is pretty traditional, using a flyback plus DC-DC. But with InnoMux-2, as you can see, we only have a single stage of flyback and two very accurately regulated outputs. And from the efficiency data over here, you can see that InnoMux-2's efficiency is just better than the traditional way across the board. For example, at 230 VAC, the efficiency gain is almost as big as 5%. Next one, let's talk about standby power performance. This design example is, again, for a constant voltage output plus constant current output for display application. And if you see the blue dotted line here is the industry requirement, where they require when the output power is 125 milliwatts, the input power needs to stay below 275 milliwatts. And this is actually by far the most stringent industry requirement, because certain manufacturers, they want to differentiate their designs from the other competitor solutions. So they keep pushing the industry requirement towards like tighter and tighter requirement. So this is by far the most stringent one. But as you can see, even with the most stringent industry requirement, by using InnoMux-2, we still manage to have a 75 milliwatts margin on top of the requirement. Okay, so that's the information about InnoMux-2, introducing you what InnoMux-2 is capable of. The next section, I'd like to talk about the exciting how does it work part, basically the technology overview. It's basically the circuit diagram for InnoMux-2 and how does InnoMux-2 work, the operating principles, and a little bit about design principles with using InnoMux-2. So let's have a look. This is an overview of the InnoMux-2 circuit, where we have a constant voltage output here and a constant current output here. Like I said earlier, InnoMux-2 works differently than other flyebacks in a way that it only steers power to the output that's requesting it. So how does it achieve that? So because we have two outputs and we want to be able to sense them and regulate them independently, that means we'll have to need separate individual feedbacks for different outputs. So over here, I have a feedback for the VCV1 constant voltage output, and I have another feedback for the constant current output here. So these are not weighted feedback. These are actually literally two feedback pins for the circuit. After getting the information from the output, we're going to have to send it back to the primary side via this thing called flux link. And then after the primary side gets the information, does all of the switching that it needs to do, goes to the secondary side. So what does the secondary side need to do differently here? The secondary side here, we're using this MOSFET here that's called a selection FET or a steering FET. That's used to steer power only to the output that's requesting it. So this controls whether power is being delivered to either the constant voltage output here or the constant current voltage output over here. Since this is a constant current output over here, that means it's crucial to sense the current as well. So I'm sensing the current through this iSense pin here. Send that information to the IC, and then the IC regulates the gate voltage of this regulating FET over here through the iDrive pin to be able to regulate the current going through this LED string. Okay, let's dive into the details of how exactly InnoMux-2 works. I'd just like to show you some demonstration of the for example, the current flow and the voltage and the current waveforms. So before jumping into InnoMux-2's circuit, I like to start with the very simple single stage, single output flyback circuit, because InnoMux-2 circuit can actually be derived from this circuit. So I've already got a 12 volt here. What happens? What do I need to do if I need another 5 volt? For example, I simply just need to add a selection FET over here. So that's my 5 volt. And at the same time, don't forget to add the blocking diode here to make sure that when the selection FET is on, my 12 volt won't backcharge my 5 volt. So this is InnoMux-2's IC, and we sense the outputs independently. Yes. What's also important is that we control the on-off of the selection FET to direct the power flow. And the control of this signal is integrated in the IC. As you can see over here, I'm actually using a single winding on the secondary side for 2 outputs. For certain cases, we have to use either stacked winding or independent winding on the secondary side. Over here, I'm only using single winding because I want to show you what the voltage on each node is. And with a single winding, it's just easier. And it helps us to see where the current should be directed to more easily. Okay, let's have a look at an example of how InnoMux-2 works exactly. So, for example, if the 12 volt drops below a reference point, then the secondary side of the InnoMux-2 IC knows that information. Then it's going to send a request for switching pulse, to switching cycle actually, to the primary side via flux link. And then on the primary side, I'm going to turn on the switch, let the current or energy build up, and then turn off the switch so that the current can be commutated back to the secondary side. Then on the secondary side, I need to make sure the SR FET is on. But, and then afterwards, because I only want to charge the 12 volt, so I need to make sure that my selection FET stays off. so that all the energy only goes to 12 volt because that is the only route. So that's my 12 volts being charged, and only 12 volt gets charged. So similarly, if my 5 volt drops below a reference point, InnoMux-2 knows that, sends the information back to the primary side via flux link, turn on the primary switch, let the energy build up again, and then on the secondary side this time, I turn on the SR, of course, and because I want to charge my 5 volts, I need to make sure my selection FET is on so that all of the energy goes to 5 volt because 5 volt has a lower potential. And if we look at the voltage at this node, when the current is being discharged to 5 volt, the voltage at this node stays at 5 volt if we ignore the voltage drop across this MOSFET. That means the voltage at this node is going to be 5 volt too. So this top diode will stay reverse bias so that, of course, again, no current will go through 12 volt. Only 5 volt gets charged. So this is how InnoMux-2 works and how we can control each output receiving energy when they need, and how we can achieve accurate regulation on each output individually. Let's have a look at some current waveforms. So over here, the red one is the VDS primary node over here. And then this one is the gate of the selection FET. These are the current waveforms. And this is the gate of the SR FET. And I know this gate SR FET of the SR FET looks a bit odd. Don't worry about it. We'll talk about why it looks like this in the coming slides later. Let's just focus on the current waveforms here. So this is when the primary current gets charged over here. Primary current gets built up. And then on the secondary side, I want the current to be discharged to the 12 volt first. That means I need to keep the selection FET off and SR on so that all the current gets discharged to 12 volt. Then for the next switching cycle, if I want the current to be discharged only to 5 volt, I need to make sure the selection FET is on, SR FET is on, all the current gets discharged to 5 volt. So we talk where all the examples over there, we use a single winding. So what's so good about single winding? This is the traditional way of getting a multi-winding flyback, where we use a single stage flyback plus a DC-DC. In some cases, or actually we have tried it from our side, we actually just basically take the transformer from an application like this and pop it into a InnoMux-2 board, and immediately we get 2 accurately regulated outputs with an efficiency gain of up to 10%. So that's exactly why we want to use single winding, because you don't have to add on any cost on the transformer. The design complexity is not high because it's still a single winding transformer, but yet you can get 2 accurately regulated outputs. So simple design, low cost, but accurate regulation and high efficiency. So why not? So over here, I'd like to touch upon the design principles of InnoMux-2. So over here, I'm saying that the reflected voltage of the lower output must be less than the reflected voltage of the top output. Why is that? That is because when the current is being discharged to 5 volt, I want the voltage to be only discharged to 5 volt. That means I need this diode to be reverse biased. That means the voltage being induced on this node needs to stay below 12 volt if I ignore this forward voltage here. So what is the voltage being induced here? That would be the voltage over here. For example, if I ignore the voltage drop across this MOSFET, then the voltage here would be 5 volts. And if you calculate based on the turns ratio, then the voltage at this node would be this one. And if I want this value to stay below 12 volt, then I work back on it and reach a conclusion of the VOR, which is the reflective voltage of the lower bottom output, needs to stay under the reflective voltage of the top output. So this is the most important design principle with using InnoMux-2, because that ensures that InnoMux-2 can operate accurately. Otherwise, it just goes back to, if you don't follow this rule, then you still have the cross-regulation issue as you would observe from a normal flyback. So that's it. That's the circuit and basic fundamental working principle of InnoMux-2. The next section, I'd like to talk a bit more about additional features that allows you to get even better efficiency and improve on the acoustic performance of your power supply. So the first thing is the further efficiency improvement by using SR-ZVS that achieves ZVS on the primary side of the switch. So by using the SR-ZVS, we can actually achieve by up to 1% efficiency improvement in the whole system. So how does it exactly work? Let's have a look step by step. So in order to achieve zero voltage switching on the primary side of the switch, what we need to do is to discharge the voltage or the energy across the switch before turning on the switch. So what we need to do is to actually turn on the SR before turning on the primary switch. Turn on the SR for a very small period of time. What this does is to create a reverse current on the secondary side of the circuit, the green one over here. So if we look at the waveform over here, when we turn on the SR FET, we can observe a reverse current over here on the green current waveform on the secondary side. Why do we need a reverse current? Because then if we turn off the SR, then the reverse current gets commutated back to the primary side, also creating a reverse current on the primary side, discharging the voltage across the VDS primary node. So the current direction is from the VDS primary node back to the high voltage rail. So by having that reverse current, the energy or voltage across this VDS node gets discharged fully. So we look at here. Due to the turns ratio, the current, the reverse current on the primary side is actually quite low, so it's quite difficult to see it from here. But you can observe the voltage drop on the VDS node here. So basically, when the voltage across the VDS node drops in nearly zero, that's when we turn on the switch, and this is where we get zero voltage switching. As you can see, in order to achieve all of this, we need to have the reverse current on the secondary side. And that means we need to have the secondary discharge current to be discontinuous first before we create this reverse current. That means we need to operate at a DCM, discontinuous mode of the power supply. What does that mean to us? Because normally designers design power supplies to operate at CCM mode, continuous mode, at low line with low line input. This is to optimize the RMS current on the primary side. But at high line, with high line input, we normally design the power supply to run at a DCM mode. This can optimize the component stress and also utilize whether it's valley switching or zero voltage switching on the primary side switch to be able to optimize minimize the switching loss. So at low line, when CCM occurs, we don't have any SR-ZVS on the primary switch. But at this point, because of the low input voltage, the voltage across your switch is not actually that high. So not having ZVS shouldn't be a problem. Okay. And also another thing is you might be asking this time over here, the turn on time of the SR or the voltage decaying time of the primary VDS node, are they fixed do I have to set it or do I have to do anything? The answer is no, they are not fixed, but you don't have to do anything either. These value, this time of the SR turn on time and the voltage decaying time, they are all adaptive. They are calculated and adjusted continuously to make sure that the SR-ZVS always operates at its optimal condition. Next one, I'd like to talk a bit about the acoustic performance of a power supply, or let's say how to improve acoustic performance of your power supply here. Acoustic performance can be quite crucial for a lot of power supply designs, especially for household appliances, because human beings can be in quite close contact with these household appliances, and it makes it easier to pick up any noise coming from it. So over here, I'd like to introduce a feature or mechanism called pulse sharing that would eliminate the audible noise caused by something called sub-harmonic frequency. So what is sub-harmonic frequency? Let's have a look first. So here I have again the example of a 5-volt and 12-volt design here. So like I said, InnoMux-2 works differently than other flybacks where it only delivers power to the output that's requesting it. So over here, under a certain loading condition, the first switching cycle, the current is being discharged to 5-volt output. But then for the next consecutive 4 switching cycles, all of the output are actually all of the energy is actually being delivered to only the 12-volt. And as you can see, this clearly creates a switching pattern that is different than the primary switching pattern. So for example, if the primary switching frequency is 40 kilohertz, then this 5-volt switching pattern that you create would only be 8 kilohertz switching frequency. This is what we call a sub-harmonic frequency. And what that does is create a lower switching frequency that might be easy for human ears to pick up, because human hearing range is from 20 to 20 kilohertz, and they can be especially sensitive around the 10 kilohertz range. So you can imagine having around 8 kilohertz might be easier for people to pick up any noise. So what did we do about it? We've introduced this mechanism called pulse sharing, and as the name suggests, we, rather than only delivering power to one of the outputs per switching cycle, we actually let the outputs share the pulse of energy coming from the primary side. So over here, as you can see, take the first switching cycle as an example. A fraction of it actually goes to 12-volt output first, and then the remaining of it goes to 5-volt. And then this continues. For each other switching cycle, it does the same thing. So that, as you can see, all of the switching patterns are actually unified now. The primary switching frequency, or the 5-volt switching frequency, or the 12-volt switching frequency, all of them are the same now. It's 40 kilohertz. The sub-harmonic frequency that we can observe from the previous no pulse sharing mode is no longer there anymore. Let's have a look at some waveforms, current waveforms, to help you better understand what's going on. Again, the red is the primary VDS, selection FET gate, current waveforms, SR gate. Nothing to say about the primary current, the yellow one. And then on the secondary side, I first want to discharge the current to the top output, which is the 12-volt. So I need to make sure that the selection FET is off. So all of the current gets discharged to the 12-volt output. And then I simply just turn on the selection FET gate over here so that the current only gets discharged to 5-volt, because we mentioned the top diode should be reverse biased in this case. And as you can see, We have 3 switching cycles over here, and each switching cycle just looks the same as the other one, completely removing the sub-harmonic frequency that we had before. And you might be asking, are these always, the sharing ratio, is it always the same? And the answer is no. The sharing ratio depends on the loading condition and is adjusted post by post in order to accommodate for any load changes. Test results over here. So again, this is a dual output application with a constant voltage output and a constant current output for display. I think this is for a TV application where humans can be quite close to it, so that they are quite stringent. They're quite tight with their acoustic performance requirement. They require below 28 dBA acoustic noise under all circumstances. And as you can see, without pulse sharing, the acoustic noise can be as high as over 38 dBA. But then with pulse sharing, the difference is huge. Even the worst case condition, my acoustic performance, my acoustic noise is still below 23 dBA. So now that we know the additional features and benefits with InnoMux-2, I'd just like to quickly introduce the applications that we can support, the different family variant of InnoMux-2. We can support many different applications, as mentioned earlier, one constant voltage plus one constant current, which can be seen quite commonly in any display or TV monitor market, where a constant voltage is used for control and constant current is used for LED string, or actually any other applications where you need constant voltage for control and constant current for any display function. So this can be seen LED lighting or HVA or any other applications too. We can also support constant voltage only output applications where we can support up to 3 outputs. And these can be seen quite commonly in appliances or industrial or any other general purpose power supplies. We can also support one constant voltage plus 8 constant current outputs. And by supporting this 8 current outputs, we'll have to use a companion or 1 or 2 companion chip from InnoMux-2 to be able to regulate these 8 constant current outputs to accurately match each other. And again, this can be seen in display markets or anything that requires a display function. We already have customers with us using InnoMux-2 in mass production. And if you're interested in starting to design with us, please go to the Power Integrations website and go look for the PI Expert online design tool that helps you design a lot more easily. Basically, you can just put your input spec and output spec, and the PI Expert software would calculate everything for you. You can tweak your design with it, and it does the transformer construction for you too, where you can just export the data and give someone the transformer construction file, and they can just build a transformer for you to start building a prototype. There are also multiple reference designs on the Power Integrations website, covering all of the applications that I mentioned earlier, including 1CV, 1CC, 1CV, 4CC, or 3CV and 2CV application. Okay, coming to the end of the presentation, I'd like to just summarize the benefits, features of InnoMux-2 and remind you again why InnoMux-2 is so brilliant. InnoMux-2 is the revolutionary single chip, single stage flyback switcher that allows you to get accurate regulation on all of the outputs without the need for any DC to DC post-regulators. That means we can achieve very high efficiency with the system with very low part count in the system and also bone count. Due to its very unique single-stage flyback architecture, it is very suitable to be used for applications with low standby requirement. And we can support many different applications, including constant voltage and constant current outputs. And the power range is up to 100 watts. So that's the end of the presentation. I'll hand it back to Colin for any questions to be asked.
Excellent. Thank you, Han, for a fantastic presentation. I'll let you give your voice a rest there for a moment before we jump in. We've got a lot of questions coming in, so do take a sip of water. Folks, we're moving to our question and answer portion of the event. If you haven't done so already, go ahead and type your question into the Q&A text area and hit the submit button. Please note that we'll get to as many questions as we can, and if we don't get to your individual question, someone will get back to you after the program is over. So, Han, I'm going to go ahead and jump right in. First question asks, is it possible to have both positive and negative regulated outputs simultaneously?
Awesome question. I get that question all the time. And the answer is, unfortunately, we cannot achieve both positive and negative accurately regulated outputs at the same time. But if you want to use an unregulated negative output, that's fine. But with accurate regulation, we're not able to do that so far, unfortunately.
All right, thank you for that. Okay, no problem, thank you. Next question asks, on slide 6, how much bleed resistance is required to maintain regulation down to zero load?
Okay, let's go to slide 6 over here. Okay, the answer is no, absolutely no dummy load at all. So there is no bleeder circuit. We go down absolutely to 0% with no dummy load.
Excellent, thank you. Next question asks, is there required any external compensation networks?
Good question. Nope, we don't need any external compensation network because we use a pulse-to-pulse control mechanism for, it's not like a traditional control loop where you need to add RC on the external circuit to kind of arrange the loop. We don't need that because it really is a pulse by pulse. Whenever you request a pulse, we send you a pulse. So yeah, no external compensation required.
Excellent, thank you. Moving along here, and folks, again, if you want to ask a question, go ahead and type it into your Q&A text area, and we will get to as many as we can. Next question asks, can we use single winding for all designs? If not, when should we use single winding design?
Good question. We cannot use single winding for all of the designs. And in terms of when can we use single winding designs, it really depends on the output voltages and the output voltage allocation. So for example, if we use a 5 volt, 12 volt, where the output voltages are not too far apart from each other, we're probably fine. Most likely we're fine with a single winding. But if we use a 5 volt and, for example, 48 volt in this case, normally we're limited by the primary side VOR of the top output. So the 48 volt VOR is, for example, limited to 150 volt. But then if we use a single winding, then the 5 volt VOR would be as low as 10 to 20 volt. And if that's the case, then your system might enter really deep CCM operation that might not be good for component stress. So yeah, really it depends. But then if your 5 volt voltage is very, very low, not the voltage. If your 5 volt power is very, very low, then there's still a chance of using single winding with 5 volts or 5 volts plus 24 volt, because you don't need that much discharging time on your 5 volts. So going a little bit slow should also be fine. So yeah, it really depends on your design's output voltage and the power allocation.
Excellent, thank you. We're going to try and squeeze a few more in here for you. I have quite a lengthy question here, so I'm going to get to the first part and just note to our attendee that we'll get to the remaining parts of this question after. But the first part says, how to apply to multiple outputs which are isolated from each other? Need to pass 1500 VAC insulation test between outputs?
Okay, that question again is an excellent question, and I get that all the time. Let's have a look at schematic over here. Unfortunately, I can't do isolation between the different outputs over here because, as you can see, we share the SR here, and all the current goes through the SR. And I sense the information going past the SR. So they really kind of need to share the same ground. So unfortunately, I can't do isolated outputs on the secondary side.
Excellent. Okay, and that again, that the remaining portions of that question will get answered offline. So thank you for that question, sir. So next one asked. Let's move on here. What's a typical switching frequency?
Typical switching frequency, it depends on the output loading condition. But normally at full load, we normally design, it depends on the primary switch tool. For the GaN part, we can allow up to 130 kilohertz at steady state switching frequency. But with MOSFET, we can only allow up to 100 kilohertz switching frequency at steady state. So yeah, it really varies depending on your load condition. But I'd say normally if you're running at, for example, full load condition, it'll run around 90 kilohertz, around 100 kilohertz with a 100 kilohertz device, or with a 130 kilohertz device, you can run up to 120 kilohertz, something like that.
Excellent. Thank you, Han. Moving along here, we've got a question. For a single winding design, how much voltage difference can be allowed? Can you do 48 volts and 2.5 volts?
Awesome question again. It depends on how much power you have on your 2.5 volt. If you have very, very little power on the 2.5 volt, so having a very low VOR on the 5 volt might also be fine. But it looks a bit far apart for me, the 5 volts and was it 40? What was the 40? How much again, Colin? I can't see it.
Yes, that was 48 volts.
48
volts.
48 might be a bit too high, but really depends on your power allocation between the two outputs. I normally recommend the top output over bottom output to be around 2.5 or less than 2.5 times difference. But if your lower output is just like 2-3 watts, it might be okay. You might have to run the actual design on PI Expert to see if it runs to CCM.
Excellent. Okay, we're going to try and squeeze in a few more here, folks. One more question. Let's see. We'll get a couple more. How is the provision of the steering selection FET different from the use of the LDO to regulate an output?
Good question. That is the fundamental difference between InnoMux-2 and a traditional flyback. Because let's think about using an LDO. You basically just chop off the energy that you don't. It's not like you don't need. You basically just chop off the voltage that you don't need and just throwing it away. But with InnoMux-2, we don't have to waste any energy. We simply just deliver power to whoever is requesting or needing it. So rather than throwing all of the wasted energy into the bin, we save all of them and utilize them accordingly. So that's the biggest difference, I would say.
Excellent, thank you. And we are going to squeeze in a couple more here. How do we determine timing to ensure SR-driven ZVS?
Okay, let's have a look at the waveforms here. Okay, so timing as in how long you need to turn on the SR FET and how long you need to let the voltage decay over here and over here. So these, like I said, they are all adaptive, but mainly it's the amount of time that you need to turn on the SR FET depends on how much energy you need to discharge over here. That's related to the input voltage, the magnetizing inductance, and the equivalent capacitance across the switch over here. So basically, you need that information. So you can read it from here, or what we do is that we actually just read it from the secondary side, the drain voltage over here, and get that information calculated inside the IC, and then come up with the accurate and correct number to set to the switching cycle to determine how long it needs to be turned on or let the voltage decay. So yeah, it really is reading the information, let the IC calculate everything, and then just get the number right. Yeah.
Excellent. Thank you. Okay, we're going to get two more in, I promise. Here we go. How does the chip determine the sharing time between outputs in pulse sharing mode?
Awesome. Okay. So the sharing between the two different outputs, like I said, is dependent on the loading condition. What that means is that the chip actually reads the previous conditions of the requesting. For example, if the voltage on this output keeps dropping and this output keeps requesting energy, then the chip is going to adjust the ratio of this output to get more energy. But then if you keep requesting even more, then it's going to give you a bigger jump of changing the in the ratio to be able to accommodate for any load step conditions. So yeah, that's that.
Excellent. And I think this is a good question to end on. When should we choose InnoMux-2 over other existing multi-output flyback solutions?
Cool. Let's have a look at. I've got this in my appendix. I won't go through item by item, but I just like to compare on a few parameters over here. Obviously, we have excellent regulation and excellent efficiency. And due to the single winding option, we can give you pretty good, a simple design of transformer, a low-cost transformer too. And of course, the system simplicity because of the single-stage flatback design. We give you good standby power too. And also EMI, this one, I know EMI is very case by case, but if you use flyback plus DC-DC, this DC-DC might run at quite a few 100 kilohertz, like for example, 500 kilohertz or 800 kilohertz. And that might be difficult for you to design your EMI filters. But with us, we don't have to use any of that. So we basically eliminate that. So really, it depends on which of these things that you care about the most. So yeah, regulation, great efficiency, simple system, part count reduction, and possibly cut in the PCB size as well. So all of that are the benefits of InnoMux-2. So when you choose your solution, look at these things and see if it benefits you.
Excellent. Makes sense to me. Well, thank you very much, Han, for an excellent presentation and a great Q&A. So to our audience, for more information related to today's webinar, please visit any of the resource links available in your green folder icon located at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So we'd also want to be sure to check out any of, again, the links in our resource folder. This webinar is copyright 2024 by AspenCore. The presentation materials are owned by or copyright by Tech Online Power Integrations, and the individual speaker is solely responsible for her content and opinion. On behalf of our guests, Power Integrations, I'm Colleen Heckman. Thank you for your time, and we hope you have a great day.